Good morning, everyone. So our next presentation is a double header. We have John Mailhot from Imagine Communications and Kunhya from Open Broadcast Systems. And they're going to be talking about ground-to-cloud media transport integration, particularly standards and approaches. And I think you're going to really like hearing the 2 points of view you're going to hear today. So please give them your full attention. Thank you.
Thank you, Wes. So we're going to be talking about the work of the Video Services Forum and the Ground, Cloud, Cloud, Ground, GCCG working group. I think last time I said if anyone's got a better name, I think we're all ears, because this is a mouthful. So during the pandemic, we saw how cloud fulfilled many of the things, compute-heavy aspects of our lives. Zoom, cloud-hosted email, social media, Amazon, Netflix, the list goes on, as we all know. But one sort of major area where this wasn't the case was television broadcast production, and pretty much all medium to high-end production is in person to some extent. But in broadcast, we'd like to use cloud economics, being able to scale up and down, in particular for sports. Sports, generally speaking, happen on a weekend, and lots of equipment sits unused during the week, for example. Let's use scale up and importantly scale down capabilities of the cloud to be able to do that. So let's move cloud production to the next level. So how do we make medium to high-end productions be possible to produce in the cloud? But I've been doing live cloud production, you say. Well, yes and no. There's lots of single vendor monolithic applications out there, plenty on the show floor, channel in the blocks, playout servers, channel switches, single vendor solutions. They use the cloud as a home, but not multi-vendor cloud solutions. There's also other mechanisms, such as with proprietary transports, NDI probably being one of the biggest ones. Those are still black boxes. They stifle innovation. They have all sorts of reasons why they're not the best solution. And this is why we're looking for a sort of open alternative. And so to get widespread adoption, we need multi-vendor interoperability via standard APIs, appropriate to task, i.e. high-quality picture levels, standards for ground, cloud, cloud, ground, and agreed mechanisms for building these workflows. And there's your classic innovators, early adopters, and early majority slides across technology adoption. What makes cloud production for television difficult? One of the big challenges is integration with the ground in both directions. There are lots of existing traditional linear television workflows. SDI, SDI2110, satellite, cable, over the air. And these workflows have very well-defined linear models. SDI, very well understood. 2110, 21, also very well understood. VBV, linear lockstep models. And unfortunately, without a proper timing model, you do end up with some kind of variable, undefined, possibly undefined latency. And this is one of the reasons web streams, they're 20 to 30 seconds behind broadcast. They don't do timing models on web. So what are my neighbors cheering about? When I cut between cameras in a production, I don't want to see a goal again from a different angle or a race car overtake it again. We need things to be tightly timed. And intercutting ground and cloud requires the same sort of timing. I'll just do 2110 in the cloud, as many say. That's not practically possible in any public cloud at the moment. There's no sort of full PTP available. Timing in a cloud is a difficult problem. Each cloud provider handles time in their own different way. Cloud networks are shared resources. They do have packet loss. Practicalities also, such as no real access to the capabilities of the network, such as packet pacing for 2110. And is this even a good idea? Do we really want linear on-prem thinking in the cloud? Whereas actually, maybe we want to be able to process things non-linearly, so go faster than real time when we can, or slower than real time now and then. On average, as long as we stay in real time, and as long as we can deliver something linear out to the end. Also, another big challenge, synthetic sources. So what happens if we have clips or material that's played out within the cloud? That has a different time source to on the ground, possibly. How do we handle that? So one of the approaches the working group is looking at is using cloud vendor-specific transport. And we have to sort of abstract away some of this transport to the cloud provider to gain the real benefits. And many cloud providers, we'll talk about that in a minute, have bulk transport protocols. And what they provide, these bulk protocols, is throughput, with reliability. So all my data arrives correctly, but also they need to have defined latency. So the first one is okay so throughput with reliability is okay for many IT applications. For broadcast, you need to also think about latency. Will all my data arrive on time? Big data, other scientific industries, other industries have needs for very large data transfers, but these often use perhaps black box protocols that the cloud provider abstracts away from you. One such example is the Amazon Scalable Reliable Datagram, SRD, and this is what's used in Amazon CDI, which is probably what many of you have in your head at the moment. So I think it's worth comparing what Amazon CDI is doing compared to what we want to do in the working group. So how does it compare? It handles a lot of the things discussed. It's an agreed way to exchange data between Amazon cloud instances, define pixel structures, metadata, a transport mechanism, HDR, etc. Amazon guarantees throughput, reliability, and they will bound latency. So in Europe, you know that all your frames will arrive within 40 milliseconds and not any later. And this is a big step forward for the industry, to be able to produce complex multi-vendor productions in the cloud. But there are parts which need this ground-to-cloud to ground input. In particular, a more detailed timing model. And in the end, CDO would be one of the mechanisms in which GCCG could be used, such as in Amazon. And so the VSF working group, GCCG working group, is addressing many of these technical problems. Personally, I think it's one of the last difficult problems in broadcast production. It's how do I do a complex multi-channel production in the cloud with some form of comparable latency to on-premises and get it back to the viewer? And there's more information available on this link there. Orchestration and control, the boring but important part, and this needs to be done both on the ground and the cloud. How do cloud instances expose their capabilities? What's the maximum resolution an instance can process? What's the maximum frame rate? What kind of orchestration layer is there to connect various instances together, to connect me to John, to Wes, to other pieces? How do we handle changes in signal flow? Lots of workflows are used to formats, resolutions changing on the fly, and the system handling that. How do we handle that? Connection status, am I ready? And ground to cloud and cloud to ground to cloud, and vice versa elements all need some level of control. So John's going to then be talking about how we're solving these problems.
Yes, the how. I mean, if you think about an SDI plant, right? You can buy Sony cameras and a Grass Valley switcher and an EVS replay and a Imagine multi-viewer, and you hook those together and it works, and you didn't even think twice about it. Because there's standards for how the SDI works, there's standards for how SDI signals the format, there's also standards, or at least industry practice, around the control system and how the routing control environment makes that all act like a system. Now, in 2110, I'd say that we're 85% of the way to the same place, meaning that you can build a 2110 system that has Sony cameras, Grass Valley switcher, EVS replay, all those same parts, but they're connected with 2110, they're advertised with NMOS, the control system pulls it all together, it acts like an environment that works, and it does. And we're building projects like that every day. But if you wanted to do that same thing in the cloud, you wanted to stand up, JPEG XS encoding to Amazon Media Connect into Panasonic Kairos, and have some cameras in the field that maybe are JPEG XS heading into that and all of that. Boy, you're in a different set of problems there, because there's not the same set of conventions and APIs and control protocols to put together that workflow. You could do it, but you'd be doing it in a very custom, very event-specific way. So the entire goal of the Ground to Cloud Working Group is to standardize the things that need to be standardized and to establish conventions for the things that need established conventions or APIs, so that you could put together that workflow the same way that you would put together a 2110 system or an SDI system. So how do we get there? What's missing, and what do we need? Well, the first thing we looked at as a working group was the operating points, especially for ground to cloud transit. How do people do it today? And there's a lot of ways. There are people that were playing with uncompressed to the cloud. At the other end of the spectrum, there were people literally taking like Zoom kind of, endpoints and putting them in the cloud. And everything was tried. We've had 3 years now of international experimentation. Well, 2.5 years of international experimentation on this topic. And there seem to be 3 operating points that coalesce. So there is a kind of bandwidth optimized H.264, usually 4208-bit, but sometimes people might do 42210. There's a small GOP, maybe progressive refresh, relatively interactive latency H.264 kind of application. NDI is maybe a variation of that, but if you just wanted to use actual standards, there's certainly standards that do that. And then at the pinnacle of picture quality, you have the premium compressed, JPEG XS at maybe 3 bits per pixel. And there's VSF TR08 that says very exactly how to do that. There's also a VSF TR09 that'll be published any day now that talks about the control APIs for that. So the good news is these things all are standards and do exist, and you can buy equipment from different vendors that implement them. Where it gets challenging is in the next layer, where you say, inside the cloud, what are the points of interoperability? If I wanted to buy a video playout server instance in Amazon from somebody, and I wanted to buy a production switcher maybe from somebody, and I wanted to buy a video processor instance from somebody, and string them together in a cloud workflow, how do they communicate? Well, maybe they use this CDI stuff, but how do they communicate from a standards and API standpoint so you could really assemble that workflow? And so what we established is that when you're going from the ground to the cloud, you have this point of interoperability that's all the way down at the bottom of the stack. It's at the IP packets, right? It's the lowest common denominator on the network. But within the cloud, different cloud providers have different underlying transport technologies. And frankly, we don't want to dabble in that. The different cloud providers, they have their own investment in that, and they have their own value add in that. So the interoperation point is kind of in the middle of the stack. It's at the buffer full of pixels level. And the buffer full of API information like, what HDR format, that kind of metadata. So that inside the cloud is the interoperation point. And then this is just the signal plane. Then you get into, as Kieran talked about, the control plane and the timing plane. That's where there's work to be done, and that's the focus of the group at this point. So what's our work in progress? Well, we've documented these premium compressed cases and published TR07, TR08, and TR09. TR07 is JPEG XS over transport stream. TR08 is JPEG XS wrapped in 211022, which is a great way to do it. And TR09 is how to take either of those and wrap them up a little more and send them over long distance, but also importantly, how to adapt the AMWA NMOS protocols to that use case, which is endpoints that are exposed to each other over a relatively unsecure network in a cooperative manner. And that's a kind of important thing that's been achieved in TR09 is that use case of the NMOS interfaces and APIs in a slightly different way than you would think about inside a facility. So that's all good work, and frankly, it's finished work, so that's great. Now, the next step is, how do we document the other cases, the transport stream, H.264, H.265, all that? And that's actually work that is starting to go on in AMWA, is to extend the NMOS to be able to describe transport streams or to describe elementary streams of lower formats like H.264. And there's an urgent need for it in the industry. I mean, transport stream was standardized in, anyone want to make a guess? What year? 95 in the New York meeting, yes. The gavel fell, so you think about that. It was 1995, that was a long time ago. The Grand Alliance system was in the test lab in Washington. I was there too. So we've gotten through, what's that, 18 years, or is it 28 years? 28 years of using MPEG-2 transport streams, and we've yet to have a public API to tell a receiver what stream to look at. That doesn't mean it's not necessary. That just means that we've suffered long enough. So that's, in my mind, one of the most important things that AMWA can work on, and I guess I have to vote with my feet and help, but Rob is just laughing at me in the back row. So the having NMOS representations for transport stream would help everybody. Now, the other thing that we're working on in the VSF is, as Karen mentioned, this time flow, time transport model. Because in the cloud, we don't want to just replicate the lockstep, everything gets synchronized to the frame boundary timing model that we've used for since, what, 1935 or something? I don't remember when television started, but if you think back to television production since before anyone here was born, it was lockstep frame. It used to be lockstep analog picosecond phasing. I mean, at least now we only worry about a half a line or so. We need to get away from that. We need to stop doing that. We certainly don't want to replicate that lockstep of frames in the cloud, but we have to replace it with something that achieves the needs of managing the latency. Because ultimately, it all comes down to latency. How long is something going to take? And more importantly, how do I bound it and how do I manage it so that each piece of equipment in the chain knows what it's getting and knows what variability it's adding to the situation? So that model and how do we treat time is, like I say, is the active work of the VSF group right now in defining it. We have a proposal, and we're in the process of writing it down. And then, of course, the fourth piece here, the media containers and what do the object formats look like. The CDI structures are defined on GitHub. They're reasonable, and we might ask or recommend some PR some tweaks to them, but by and large, they're nice, and there's no point in messing with them too much. So, what is this time variability work? Well, we need to allow variability, but we need to put bounds on it. And you have to understand that at the end of the chain, suppose you have a whole bunch of things in the cloud and the signal passes through a bunch of them, there's going to be something like, say, an MPEG encoder at the back end of that chain that's trying to create a linear presentation model. And it needs to know how much delay to add in its front end to accommodate all the things that happened upstream. Now, the way the OTT encoding world works is they just add a lot of delay, and they hope. We'd like to have a better strategy than hope. So that's the objective here in this timing model, is to be able to predict the worst case amount of delay that stream elements could have when they come together. Now, where do things come together? Well, they come together either in a process that needs to linearize them, typically an encoder, or in something that needs to do an operation on more than one thing, like a switcher or a master control switcher that needs to be able to take the A bus and the B bus and do a proper crossfade or whatever. So all those operations have a need to time reconcile two signals or to time reconcile an incoming signal to a linearized timeline. Now, the first step is vocabulary. We have to figure out what do, literally words and what do we mean by them. So we talk about transmit variability, we talk about planning delay, what's the baseline amount and what's the actual delay. And then we have these equations and models. So devices literally have what's the minimum latency through a process step and what's the, variability on top of that. So we think about the, what we call the minimum delay, and then the, 99% of the time the delay is no worse than this kind of thing. There's always an outlier, but that can be handled offline. It's getting the 99% case handled. And then how do you compose those? So if you make a chain of things, how does the timing of the end get composed out of the timing of all the parts? And it's math, but it's not bad math. It's just when you write it down and you write down meanings of the words, it's like high school algebra all over again, and it kind of makes sense. So that's what we're doing, is going through the process of writing this down and making it formalized so that equipment could be tested against it and so forth. So we've achieved some consensus views. We've achieved, we have a consensus on targeting TR08 and 9 for high quality. and targeting H.264, 265 kind of transport streams for intermediate quality. We have consensus around for inter-instance handoffs. So between cooperative elements within a placement group, if you're using AWS terminology, or within whatever other people call that sort of thing, having a way to identify senders and receivers, again, using a suitably extended NMOS model, which would be NMOS exposing CDI endpoints. Straightforward to do, just needs writing down an agreement. And then the description lingo. So in the ISO 4 and 05 exposures of these things, having definitions around the timing and all the other stuff that currently goes with the signal, like colorimetry and so forth. Well, those things exist. And then, of course, the canonical buffer style, again, exists. There are some proposed variations. Maybe they'll take on, maybe they won't. And ultimately, the control API model, by leveraging the existing work of AMWA and just suitably extending it for these different transports and different packaging formats, we think we're going to be able to get done very quickly, because we don't have to reinvent the wheel. We just have to establish the pattern of the holes and the thread of the lug nuts. So that's sort of the consensus views and how we're moving it forward. The group is working on the documents right now. There's parallel work in AMWA on extending NMOS to these different essence formats and different transports. TR08's published. TR09 is any day now. And these groups mainly need more interested participants who are willing to put a shoulder to the wheel and push a little. So you can join the VSF, you can join the AMWA. I think there's even information here in the room on how to do that. That's how you get involved. So thank you all. Are there any questions or comments, or stump the non-experts? Be glad to hear it.
Any questions? Anybody?
Any heckles or complaints? For people who believe we're doing totally the wrong thing.
Can you hear us? All right.
Thank you
very much.
Thank you.